Hello everyone! For this video, we will be discussing Newton's polynomial. So Newton's polynomial is sometimes called the Newton's divided differences interpolation polynomial because the coefficients of the polynomial are calculated using Newton's divided differences method. So later on, we will be discussing and you will know what does the divided differences interpolation polynomial means. So in this video, we also need to discuss the formulas that you need to remember or the formulas that we will be using in solving for the Newton's polynomial. So the nth order polynomial of Newton's divided difference interpolating polynomial can be solved with using this formula. We have fn of x b sub 0 plus b sub 1 is multiplied by x minus x sub 0 plus so on and so forth until the nth power of our polynomial. So you need also to remember that BO is equivalent to f of x of 0 and B1 is equivalent to f of x sub 1 and x sub 0. So later on, we will be applying this one in an example so that you'll see how to solve the Newton's polynomial. So there's also more formulas that you need to remember. First one is you need to remember the first divided difference formula, which is equivalent to this one. First divided differences contains x sub 1 and x sub 0, in which you need to substitute the value of our x sub 1 minus x sub 0 to our function and divide that by the original value of our x sub 1 and x sub 0. The same goes with second divided difference, in which this is the subtraction between the result for x sub 2 and x sub 1 and x sub 1 and x sub 0. So I think there's just a typo here. This one should not be minus. This one should be the same as this one, which is comma, separated with comma. And that will be divided by the original value of our x sub 2 subtracted by the original value of our x sub 0. And for the nth order divided difference, you just need to follow this one, or you must need to follow the sequence in solving for the divided difference. So that being said, we have this formula here in solving for the nth order of our Newton's polynomial. So we have f sub n of x is equivalent to f of x sub 0 plus f of x sub 1 and x sub 0 multiplied by x minus x sub 0 plus f of x sub 2, x sub 1, x sub 0 multiplied by x minus x sub 0 and multiplied another 1 by x minus x sub 1 and so on and so forth. So now we will be discussing this one. We will be applying all the formulas that we have discussed in an example. So we have here example: fit a second order Newton's polynomial to estimate logarithm of 10 using the given data points x is equal to 8, x is equal to 9, and x is equal to 11. So in this case, in order for us to continue, in order for us to start, we just need to find the value of our x sub 0, x sub 1, and x sub 2 first. So given these data points here, these are the values that we'll be using for our x sub 0, x sub 1, and x sub 2. And as you can see, this is in second order Newton's polynomial. So later on, we'll be solving for the second order of our polynomial. So First, writing our x sub 0. X sub 0 is said to be equivalent to 8. X sub 1 is equivalent to 9. X sub 2 is equivalent to 11. And then, substituting this one to our function, as you can see, this will be our basis for our function. So, meaning to say our f of x is equivalent to log x. Now, from that, we need to substitute the values of our x sub 0, x sub 1, and x sub 2 to our x. So, that being said, we have f of x sub 0 is equivalent to log of 8, which is equivalent to 0.90309. And also, you need to remember that you need to use 5 or 6 digits, 6 decimal places for your answer. And the same goes with x sub 1. We also need to substitute that here. So that gives us log of 9 is equivalent to 0.954243. And for our log of x sub 2, which is equivalent to 11, is equivalent to log of 11 is equivalent to 1.041393. So these are now the values that we'll be using later on for the substitution to the formulas that we have discussed earlier. So now the first thing that we need to do is, after we get these values, we need to evaluate the first divided differences. So in order for us to get the first divided differences, we need to use these two values. So first, we need to find the f of x sub 1 and f of x sub 0. So that being said, that as we know from the formula earlier, that is f of x sub 1 minus f of x sub 0. Again, we have f of x sub 1 minus f of x sub 0 all over the original value of our x sub 1 subtracted by the original value of our x sub 0. So that being said, we have here this one, the f of x sub 1. So we have 0.954243 minus the value of our f of x sub 0, which is 0.90309. Divide that by the original value of our x sub 1 and x sub 0, which are this one. So we have 9 minus 8. So that gives us the result of 0.0511. I'm sorry, we have 1153. So if you try to calculate this one, you'll get this result, the 0.051153. Next is, after getting that, we also need to find or evaluate the first, we need to also find the first divided differences of x sub 2 and x sub 1. So that being said, we also need to solve for that one. So we have x sub 2 and x sub 1 is equivalent to the same process. We have f of x sub 2 minus f of x sub 1, multiply both sides, divide overall by x sub 2 minus x sub 1. So that gives us the result of, we have 1.041393 minus x sub 1, which is 0.954243. Divide that by the original value of our x sub 2, which is 11 and 9. So that gives us the result of 0.043575. So that is for the first divided differences. Now, we also need to find the second divided differences. So for the second divided differences, we have here f x sub 2, x sub 1, and x sub 0. So from that, we have the formula f of, we have f of our x sub 2 and x sub 1 minus f of x sub 1 and our x sub 0 divided by the original value of our x sub 2 and our x sub 0. So that being said, we have here, as we know, this is our x sub 2, x sub 1. This is our x sub 1, x sub 0. So we need to substitute the result of that one here in our equation. So we have 0.043575. So here, we need to substitute our x sub 2, x sub 1 here in our equation, and that is subtracted by f of x sub 1, x sub 0. So we have 0.051153 divided by x sub 2, which is 11, minus x sub 0, which is 8. So that gives us the result of negative 0.0025, we have 526. So this is the result of our second divided differences. So again, these two here are our first divided differences, and this one is our second divided differences. Now, substituting all of these values to our Newton's polynomial equation, which is equivalent to, so again, we have the Newton's polynomial equation, which is equivalent to, since we are looking for the second order, so we'll just stop with the second order. So we have f of 2, f sub 2 of our x is equivalent to our f of x sub 0 plus our f of x sub 1 and x sub 0 multiplied by our x minus x sub 0 plus our second divided differences, which is f of x sub 2, x sub 1, x sub 0, and that is multiplied by x minus x sub 0 and x minus x sub 1. So again, this is the formula in getting the second order of our Newton's polynomial. So from that, since we already have the values of all of this, the values of this one, so we can just substitute that to our equation. So we have here the result for f of x sub 0 is, as we know, this one. So you just have to substitute that here. So we have 0.90309 plus our f of x sub 1, x sub 0 is this one, right? So you just have to replace that here, which is 0.051153 multiplied by our x minus our x sub 0, which is this one, the 8. This one, our x of 0, which is 8. So that's 8. Plus our f of x, which is this one. So again, substituting that here in our equation. So this will become minus 0.002526. Then we have the x minus our x of 0, which is 8, and our x and x sub 1, which is 9. So from that, as we know, we cannot solve this one yet because we don't have the value of our x yet. But from our problem, we have here fit a second order Newton's polynomial to estimate log 10. So meaning to say, if our function is log x, so meaning to say 10 here is our x. Now from that, we can already substitute our x by 10. So at x is equal to 10, we can already solve for our Newton's polynomial. So that gives us 0.90309 plus 0.051153. That's 10 minus 8 minus 0.002526. That's 10 minus 8 and 10 minus 9. So if you try to calculate this one, maybe say this is our f sub 2 of 10, f sub 2 of 10. That is equivalent to 1.000344. So from that, meaning to say we already have the answer for our Newton's polynomial. So this is the solution for this problem above. Fit a second order Newton's polynomial to estimate log 10 using the given data points. X is equal to 8, 9, and 11. So those are all the discussions for the Newton's polynomial. So I hope you understand the lesson, and I hope you try to solve on your own, find any problems from the internet, find any problems from a book, and try to solve that in your own. So thank you very much and have a great day.